All right, let's talk about programming. We're going to completely demystify it today. My goal here is to show you that it's not some kind of dark art or cryptic magic. It's actually a really powerful and, believe it or not, a surprisingly accessible way to solve problems. So, let's dive right in.
You know, it's a super common belief, right? We all have this mental image of a coder, kind of like a lone genius, maybe a math prodigy who just gets it. But you know what? That whole intimidating image, it's pretty much a myth.
Because at its very core, programming is for anyone who likes to solve puzzles. It's for people who can look at a challenge and break it down into logical, manageable steps. Look, if you can think things through methodically, guess what? You've already got the most essential skill you need.
Okay, so first things first, let's just tear down some of those big myths that tend to scare people away from even trying to code. We're going to replace them with what's actually a much more approachable reality.
And this right here, this is the key to everything we're about to cover. The single most important skill isn't about memorizing a bunch of weird syntax or being some kind of math wizard. It's all about your ability to structure your thoughts in a logical way to get to a solution.
This slide really lays it all out, doesn't it? The myth is you have to be this math expert, but in reality, most of what you'll do just needs basic logic. And the idea that you have to memorize everything? Nope. Professionals are looking things up in the documentation all the time. And that whole Hollywood hacking thing you see in movies, forget about it. Real programming is just about giving careful, step-by-step instructions. So, if it's all about giving clear instructions, how do you even come up with them in the first place? You don't just, sit down and start hammering out code. The best programmers are amazing planners. They always create a blueprint for their logic first.
And that blueprint, well, that has a name. It's called an algorithm. And honestly, the best way to think about an algorithm is just like a recipe. You've got your ingredients, that's your data, and you've got a list of super precise step-by-step instructions. You follow them correctly, you get the result you want, whether that's a perfect chocolate cake or a perfectly functioning app.
And here's the cool part. Programmers have actual tools to help them write these recipes. They'll use things like pseudocode, which is kind of like writing out the steps in a simplified, structured English, and flowcharts, which are basically visual maps of your logic. This planning part is where the real problem-solving happens, way before any actual code gets written.
Now, flowcharts are awesome because they use this really simple visual language to map everything out. You don't need to be an artist. The key thing to know is that different shapes mean different kinds of actions. Like, an oval means start or stop. A rectangle is for doing something, like a calculation. And the diamond? Well, that's where you make a choice. Let's look at a super simple example. A flowchart that finds the bigger of two numbers. See? We start, we get the two numbers, and then we hit that diamond, the decision point. It asks a simple question. Is the first number bigger than the second? And depending on whether the answer is yes or no, we follow a different path to the end. It's a crystal clear map of the logic. Okay, so once you have your logical blueprint, you're ready to build. And you build your program using just a few fundamental pieces. I want you to think of them like Lego bricks. Seriously, they're simple, standard pieces, but you can combine them to create almost anything you can imagine.
Okay, first up we have the variable. It's really just a named container for a piece of info. That's it. Imagine you label a box user's age, and you put the number 30 inside. If you need to change it later, you just swap out the number. It's literally that simple.
Next, we have conditions. This is how your program gets a brain, basically. An if-else statement is just like coming to a fork in the road. If the user is logged in, then show them their dashboard. Else, show them the login page. See? This is how programs make smart decisions.
And finally, we have loops, which are all about being efficient. And honestly, this might be the big aha moment for you. Loops pretty much run the modern world. That endless scroll on your social media feed, that's a loop. An enemy in a video game that's constantly checking your position, yep, that's a loop. They're the absolute powerhouse behind any task that needs to be repeated. So, let's recap. These three things, variables to hold your data, conditions to make choices, and loops to repeat tasks, these are the fundamental building blocks of almost every single program out there. If you can really get your head around these concepts, you've mastered the core of what programming logic is all about.
All right, so let's say you've done all that. You've built this perfect logical recipe using your variables, conditions, and loops. But hold on, there's a big problem. You've written this in a language like Python or C++, which is something a human can read. How on earth does the computer, which only understands the raw language of ones and zeros, get the message?
Well, that's where our translators come in.
There are two main types of programs that exist to bridge this huge gap between your human-readable code and the machine's binary language. They're called compilers and interpreters.
And here's a fantastic way to picture this. A compiler? It's like a book translator. It takes your entire program, your whole book, translates the whole thing at once, and then hands you a completely new, fully translated version. An interpreter, on the other hand, is like a simultaneous translator you'd see at a big conference. It translates and acts on your program line by line as it happens, on the fly.
So on one hand, you've got compilers, which are used by languages like C++. They translate everything up front, which makes the final program run incredibly fast. On the other hand, you've got interpreters, which are used by languages like Python. They translate as they go. Now this is a bit slower, but it makes developing and finding bugs way more flexible because you get instant feedback the second something goes wrong.
Okay, let's zoom in one last time, right down to the microscopic level. Whether your code was compiled or interpreted, it eventually becomes a series of really simple instructions. So how does the brain of the computer, the CPU, actually do the work?
And you're not going to believe this, but deep down the process is, well, it's a lot like a super fast deli worker handling your lunch order. Your CPU is unbelievably fast and efficient, but at its heart, it just follows a very simple, repetitive cycle for every single little instruction it gets. This right here is the legendary fetch, decode, execute cycle. First, the CPU fetches an instruction. That's like our deli worker grabbing the next order ticket. Second, it decodes that instruction to figure out what needs to be done. Our worker reads the sandwich order. And finally, it executes the command. It actually makes the sandwich. This simple three-step cycle happens billions of times every single second.
And that brings us all the way back. Programming isn't magic at all. It's really the art of creating a clear, logical recipe, your algorithm, that a very literal but incredibly fast machine can follow step by step to get something done.
So you see, programming isn't some secret club. It's built on these simple, logical ideas that anyone can grasp. It's an incredibly powerful tool for every problem solver out there. So I guess the only real question left is, what problem are you going to solve first?